Okay, so we're going to draw several things here. We're going to draw representative sample vectors of the gradient field. Then we're secondly going to draw the graph of that function. And then we're just supposed to note that the gradient field always points uphill in the graph. So you can take that as this is what we're supposed to do after we've drawn the two things, or you can take this as a hint to help you draw these two things. Is that, let's not forget the gradient field always points uphill on the graph. Okay. All right. So let's take these one at a time. Let's start with the graph, just because it's more basic. Right. Okay. So here's our function. The graph, of course, is what you get when you set the output equal to z. And so how do we draw this picture? Let's see here. Well, so this picture has let me talk about level sets of this picture. When x plus y is equal to a constant, we always get the same value of z. Right? So we can turn that observation into some part of the picture. So I guess I'll draw it over here. So when x plus y is a constant, there's x plus y equals 0. All of those points have the same value of z, and in particular, when x plus y is equal to 0, sine of 0 is 0, and so the graph is, here's a bunch of points on that graph. Okay. And then repeat for different values of x plus y. As you look at different values of x plus y, you're going to get different lines, all parallel, right? And as you move more in that direction, then the argument of sine gets bigger and bigger, and so you're going to follow the pattern that sine does, which is up and then down, then up and then down. Okay, so let's see here. Let me try to draw this then. So you get one there, and then this is mostly an art thing at this point. That didn't go over far enough. Can you see those purple lines sitting above the green lines? Yeah. This is one of these situations where, I did that thinking that would make the picture look better, but I think I've learned something from having drawn that, but now that I've drawn it, I feel like, but I can see now a better way to draw what I'm trying to draw here, which is, let me get rid of all this colored stuff, and, let me just get rid of all this. This is just ended up being a kind of a mess, but I learned a lot there. But here comes a better picture. Oh, man. Well, it's hard to erase those without erasing everything else. But I'm just going to draw now. There's that, and then look, it comes up and goes down, and it comes up and goes down like this. And so that's easier to see. Mm-hmm. So we learn something from the first drawing, and then realize that here's a better drawing. And then it's going to continue on, of course. It's going to continue on. Oh, of course, I ran out of space, but so it continues up and down. Yeah, everybody happy? Okay. So that's what the graph looks like. Now let's talk about the gradient. Of course, the gradient is in the domain. Let me write down the algebra here. Okay, so the gradient field for this, gradient f, is, so the x partial is cosine of x plus y, and the y partial also cosine of x plus y. Yeah? Everybody good? And let's draw this. Now, well, that's a weird vector field to try to draw. But it's easier to draw when you make this realization that it's cosine of x plus y times 1, 1. And that really helps. Because 1, 1 is, that way. It's always pointing in the same direction. It's a constant vector. Okay. So what this says is that our gradient vector, let me do this in maybe blue. Our gradient vector, it's always pointing in the 1, 1 direction, but with its magnitude, well, with the multiplier varying depending on what x plus y is. So let's, again, plug in a few values. What if x plus y is equal to 0? So when we're on that line where x plus y is equal to 0, cosine of 0 is 1, and so we actually get 1, 1, so we get a big vector pointing in that direction. Notice that points uphill on the graph, right? Okay. All right, now for artistic, so our picture doesn't get too cluttered, let me just draw the next vector after having erased the previous. So here we have x plus y equals a slightly larger value. Well, cosine is going to be smaller. Still positive, but smaller. So we're going to have these shorter vectors. No problem, see ya. And so that still points uphill, but you'll notice it's shorter. Is it okay that it's shorter? Well, yeah, sure, because the steepness up here is not as great as the steepness was over there, right? And the steepness is indicated by the magnitude of the gradient. Okay. And then, etc. Keeps going. Let's see here. So what about, here, sitting right above the sort of the crest line here, the ridge at the top? Well, that is where sine of x is 1. That means that's where cosine of x is 0, which means that the magnitude of the gradient vector is 0 on these points. And, well, that makes sense because there is no uphill. We're already at the top of the hill. Proceeding. Let's look at, let's just skip overhead to this point. That's where x plus y is equal to pi, which means cosine is -1, and if that's -1, then we have negative. And so even though it's, -1 times that vector, well, yeah, but uphill is in that same backwards direction, so we're again, it's still pointing uphill. Right, and then repeat. So now I didn't give myself enough space really to draw a good picture there. An argument could be made that this should be a very large picture. I would encourage you to take an entire sheet of paper to try to draw this picture, just because if you want to draw all of these vectors all at once, I didn't do that, right? I just drew sort of some of them, little bits at a time, and this picture being as small as it is, it's going to be hard to fit all those vectors all at once. So, but if it's a nice, great, big picture, then you've got more room to draw those vectors.
So it would look something like this, right? The bottom one?
Yeah. That's right. That's right. And see if you can draw that, though, on the three-dimensional context, so you can see how they relate to the uphill direction on the graph.
Do you want us to draw it on a three-dimensional?
Well...
Will that be for just to see the relation?
Yeah, that's just to see the relation, but in order to see the relation, you need to have the drawing. To see means suggest visual. Visual means you're looking at something, and the something in question is that picture. So, I think it'd be better to actually draw this kind of a thing here.
So is this a good method to finding the gradient field, or could you apply this to other fields?
Well, no, the easiest way to see what the gradient field is that, right? My intent here was just for students to see that the gradient field has this feature that it everywhere is pointing uphill with magnitude equal to the slope. It's just really, so there's this very strong connection between the gradient field and the graph in that sense. I just wanted students to make that connection. Oh, yeah. But in terms of computations, the way you compute gradients is pretty straightforward. Mm-hmm. Yeah.
guess by looking at the graph, you can see what your field should look like.
Yeah, sure, right. That's right. I mean, if you don't know, for example, what the maybe you don't know what the function is, and all you know is what the graph of the function looks like, then yeah, that's right. You can draw a conclusion. You know, at that point there, okay, well, I can see which direction is uphill, and I can see about how steep it is, and so I bet you the gradient vector is kind of like that. Totally. Cool. All right.